Great. So this week we're going to start off by looking at section 4.1. So we're going to take a look at what are called rational functions, which are basically functions that have a fraction. So functions that have fractions. So problems that we look at, let me show you an example, are going to look something like that. Okay. Rational functions can have a variable in the bottom. Sometimes they also have a variable in the top, okay, like that one. But it's always going to be some kind of fraction with a variable in at least the top or the bottom. So both the top and the bottom will be polynomials, which means you can't have any exponents that are negative. Okay? You can have things like this. Okay, that's an example of a polynomial. You can have fractions, okay, that are numbers. So you can have something like, that's fine. Okay, that's a polynomial. Okay, basically anything that's linear, quadratic, cubic, okay, all those different terms that we talked about when we described polynomials by their degree. Okay. What you can't have is something like this. Nope, can't have a square root. Okay, if it has a square root, that's not a polynomial. That's pretty much the only thing we're going to have to look out for, but you're not going to have any with square roots. Now, you can have any polynomial in the top and any polynomial in the bottom, except there is one thing we're not allowed to put in the bottom. What are we never allowed to put in the bottom of a fraction? Zero. Okay? So that's the only polynomial that you can't put in the bottom, would be the polynomial 0. And yes, technically polynomials can just be a single number. Okay, zero is a polynomial, it's a constant polynomial. There's another example of a rational function. This is a quadratic polynomial in the top and a linear polynomial in the bottom. Here's another one. That's a quadratic over a quadratic. All right. So when we look at polynomials, sometimes we just want to get an idea of kind of the big picture, okay, of what this thing would look like if we zoomed out. So let's just look at this top one for a second. Okay, forget about the bottom for now. Just look at the top. Okay, I'm going to graph that in y1. So I've got 3x squared minus 4x plus 1. Okay, I'm going to do zoom 6. And that's what it looks like. Now, I'm going to graph just this, just 3x squared. And I want to see what happens. Okay, it's not going to look identical, right? Because it's different. But let's see how it looks. Okay. How do they compare? Are they completely different? Are they kind of close? What do you think? Yeah?
They have the same general shape at different locations.
Yeah, they have the same kind of general shape, but one's moved a little bit because these other terms that we didn't graph, they did affect it a little bit, but they didn't affect the overall shape. So whenever you want to get an idea of generally what something is going to look like, all you have to do is really graph the term with the highest exponent. And if you graph that, you'll get a general idea of what your graph is going to look like. Okay. This term right here is called the end behavior model. It's called the EBM. end behavior model. Basically, it describes what the ends of the function are doing. In the original function, that was the one in blue, it's going up on the left and it's going up on the right. And that's exactly what the red one is also doing. It's going up on the left, up on the right. Okay. Let me do one more. Let's graph 2x cubed minus x plus 3. Okay, so this one's a little different. This one is going down on the left side, but then it's going up on the right side. Now, let me just graph the first term. Okay, let's forget about the minus x and the plus 3. Let's do 2x cubed. And let's see if this red one also goes down on the left and up on the right. What do you think? Does the red one match the overall shape of it? In that case? You think, right? Yeah, so we're not, when we look at what's called the EBM, we don't really care about what's happening in here. Okay, so we can just kind of even block that out. Don't even look at what's happening in there. All we care about is what's happening on the ends, okay, as we go left and right. If we just look at the ends, do the ends look pretty close? Yeah, and that's all that this term is supposed to do. This end behavior model is just supposed to give you a quick idea of what the ends are going to look like without all the extra details in the middle. That's what this does. Okay. So any questions on how you find the end behavior model? Okay. So what if I had one like this? What would be the term that I would graph there if I just wanted to get a quick idea of what that would look like without all the details in the middle? Yep, 4x to the fifth. Exactly. Again, is it going to look identical to the top one? No. There's going to be little details that are left out. But if you just want to get like an overall kind of simplified picture, just graph the term with the highest exponent, because that term controls the whole thing. Right? Biggest exponent, think of it, it's always the most powerful thing. Right? That's what's going to control what it looks like. These other terms just control little details in the middle, but we're not concerned about those when we're looking at the big picture. Okay? All right, so how do we find the domain of rational functions? What did we say earlier that you're not allowed to put in the bottom of a fraction? Yeah? 0. So the domain is any value that you can plug in as long as that does not make the denominator 0. So in order to figure out the values that make the denominator 0, we just take the denominator, set it equal to 0, and solve it. Whatever you get when you set the denominator equal to 0, you have to tell me not to use those values. Okay, we don't want to divide by 0. Okay, so let's try this one. Find the domain of the following. Okay, so for the domain, we always start out with all real numbers, and then we eliminate anything that you could plug in that would cause you to divide by 0. So is there anything here that we would not be allowed to plug in for x? Yeah, 3. Yeah. So the domain is all real numbers except 3. If we want to think of that as a picture, okay, on a number line, you want to graph it. Can you pick numbers lower than 3? Would that be okay here? Yeah. Yep. So you can pick anything you want that's lower. Could you plug in numbers higher than 3? Yeah, that's fine too. So you can plug in anything higher than 3. You just can't pick 3. But you can go anything lower and anything higher. And so this is in words. This one is a graph. And let's do it one more way, describing the domain in interval notation. When you do it in interval notation, think of your graph and think of, is this line on the graph connected? Like, could I draw the shaded part without ever lifting my pencil? What do you think, right? No, we can't, right? Because there's a gap in it right here at 3. So we've got part of the graph that we shaded is over here, and then we lifted our pencil, and the other part is over here. In part 1, how low does that part go? Negative infinity. Yeah. Can you ever reach negative infinity? No. So the lowest that part 1 goes is negative infinity. And how high does part 1 go? But it doesn't include this number. Part 1 doesn't go all the way to infinity. We got 2 separate parts. Yeah? It goes up to 3, but we cannot include it. Okay, so that describes all the numbers in interval 1, everything from negative infinity up to 3. And then in part 2, how low does part 2 go? 3. Can we include 3? No. And how high does part 2 go? Infinity. That describes all the numbers in the second section of the number line. So this is everything below 3 in part 1. This is everything above 3 in part 2. And we have to put a symbol between them. That symbol means or. When you write something in set notation, they generally don't write the word or. They use the symbol in math for or. Okay, the name of that symbol is union. That's the name of it. It means or. Okay, when we describe the domain, we're generally not going to do it 3 different ways. But I'm just showing you if they ask for it in words, a graph, or what's called set notation. Those are the 3 different ways. Okay, and I think we've looked at set notation before, right? Yeah. In case anyone doesn't remember, this is the lowest value you can have, and that's the high value. It's always low, comma, high. It's going to be in that order. Okay, let's try this one. So this time we have 2 quadratics, one at the top, one at the bottom. But we've got to do something to the bottom to make it easier to see. What numbers could you plug in that would make it 0? It's not easy to see right now, at least not like the first one. What's something you can do to a quadratic that makes it easier to see what would make it equal to 0? Besides quadratic formula.
Solve.
What's that? What's another way to solve it besides quadratic formula? So once you put something in this box and make it equal to 0, what's the method you can use to now solve it? Not substitution. Generally we do that when we have a system of equations. So you'd have to have 2 equations with 2 letters. Okay, how could we simplify it? By one?
Getting together like 3x to the second combined with x to the second.
Well, these aren't like terms, right? So we can't combine those together. It's not like you have like 3x plus 2x and you can just say 5x. So there's only a couple different ways we can solve something that's a quadratic. One is quadratic formula, which we're not going to do on this one. But what's another method you can use if the numbers work out nice? Begins with an F. Factor, yeah. So what you want to do here is factor the denominator. And that will make it easier to figure out what numbers you can plug in to get 0. Okay, when we factor it, what's going to be the first term in each set of parentheses? Yep, so we're going to need an x and an x. Now I have a positive in the middle, and I have a negative for my constant. So what's going to be my signs inside the parentheses? Yep, I need a plus and a minus. And now I need two numbers that multiply to give me 2, but it does matter which one I put where. So what would be two numbers that multiply to give me 2? 1 and 2. And I'm going to do them in that order. Okay, let's check it. So now if you multiply this back out, you'd have x squared minus x plus 2x. What's negative x plus 2x? X. And that's exactly what we had in the middle. And 2 times negative 1 is negative 2. So we're good. We factored the bottom perfectly. Okay. So now, what values would you not be allowed to use in the bottom? And this time there's 2. Negative 2 and what? 1, yeah. So the domain is all reals except negative 2 and 1. And if you were going to do that one as a graph, can you pick numbers lower than negative 2? What do you think, Lucas?
Yeah.
Yeah, you can pick numbers lower than negative 2. That's fine. Can you pick anything between negative 2 and 1? Would that work? Yeah. Remember, there's only 2 numbers you can't pick. You can't pick negative 2 and you can't pick 1. You can pick something between them, like 0.5, 0, 0.7, negative 1.3. Any of those are fine. We just can't pick these 2. And then can we pick numbers higher than 1? Yeah. So that's what your domain would look like as a graph. And how many pieces do we have to this domain? If we wrote it in set notation. 3, right? It's 3 separate pieces. Anybody think they could tell me how to write the leftmost piece? Any number lower than negative 2.
Parentheses,
Mhm.
negative infinity,
Yep.
and the comma, negative 2 parentheses.
Perfect. Right? That's how you describe all the numbers in the first section. Or, now we have this middle section. What's the lowest number in the middle section? Negative 2. And what's the highest number? 1. And can you pick either one of them? No. If you could, you'd put a bracket. But we can't. So we use a parenthesis. So it's everything in the second section. And the third section. What's the lowest number there? 1. And the highest number? Infinity.
Will there ever be brackets?
Well, you never put brackets on infinity because you can't reach it. And you don't want to put brackets on these numbers because then if you put a bracket, that would mean to fill in the circle, which means you can use it. And we don't want to use it.
So never use brackets.
Not when you're finding domain, no. Nope. Okay. Any questions on that one? And this would probably be the most complicated one we would have, where you have to write 3 sets of parentheses. This one would be a little simpler, where you only had to write 2. All right, let's try one more of those. This time it's already factored for you. And I'm just going to write this one in words. I'm not going to show all 3 ways this time. How many values are we not allowed to use? 2. Yep, there are 2. And what are the 2 values? Right. You can plug any number you want in for x. Just don't plug in a 2 or a negative 4. all reals except 2 and -4. Okay. So any question on finding the domain of those? Okay. So these are all rational functions. Polynomial in the top, polynomial in the bottom. In this case, they were both quadratic. In example C, the bottom would be quadratic if you FOILed it out, but the top has an exponent of 3. What do we call a polynomial that has an exponent of 3? What is it? Cubic, yeah. So this was a cubic over a quadratic. Okay, so these are kind of complicated ones to draw. This is the simplest rational function you can have. 1 over x. It's called the parent function. And all other reciprocal functions are basically some modified version of that. More complicated numerator and denominator. Okay, but that's the simplest. Okay, let's graph it. What number are you not allowed to plug in for x in this case? 0. Okay, so let's graph it. And you'll watch, kind of see what happens when you get close to 0. Watch what the graph does. Okay, now it's not perfect because the calculator kind of makes it look like this graph doesn't go on forever, up and down. At least to me it does. It looks like it kind of just stops. It shouldn't just stop. Okay, so this graph on the left side continues curving down without ever touching the y-axis. And this one continues up. So that's what your graph looks like. A lot of these graphs have sections in them that get very steep. When a graph gets steep, the calculator kind of gives up drawing. Sometimes. Right? That's what it looks like. Okay, so let's look at 2 things. This part right here, as x approaches infinity, this means as you head to the right. Think about what direction infinity is on the x-axis. Okay, that's to the right. So as you head to the right. What do you think it means if x is heading towards negative infinity? Right. As you head to the left. Okay, that's what those 2 things mean. So it's just 2 different directions on the graph, as you head to the left and as you head to the right. Okay. So I want to look at what happens to y, okay, as you head left and you head right. Let's start by heading to the right. When you head to the right, you're on the top piece. What's happening to the y value the further and further right that you go? What does it look like it's getting close to? Yeah, it's getting very close to 0, but it's never going to reach 0. It's just going to get very, very close. And it's coming down towards 0. Now, let's look at what happens as we head to the left. What does it look like we're getting closer and closer to as we head to the left? 0 again. The difference is we're heading up towards 0. Heading up towards 0. So as you head to the right and as you head to the left, the y value, remember f of x is just another name for y, the y value is approaching 0. Okay, any questions on that? Now, if you look at it without the picture, just think of this this equation, this fraction. 1 divided by x. If x is 100, what's 1 divided by 100? 100th, right? 0.01, very small. Now let x get even bigger. Let x be 1,000. What's 1 divided by 1,000? 1/1000th. Okay, that's even smaller. So the bigger and bigger that you continue to make x, the smaller and smaller this entire fraction is going to get. That's what that means. And it works both if you make x a really big positive or a really big negative. If x is negative 100, you get negative 1/100th. If x is negative 10,000, you get negative 1/10,000th. So the bigger you make x, the closer you get to 0. But even if you take 1 and you divide by 10 million, is that ever going to be 0? No. The only way a fraction can be 0 is if you start with 0 in the top. You're starting with 1 in the top. Okay, so no matter how big of a number you divide 1 by, it will never hit 0. Okay? Because you never hit 0, that horizontal line is called an asymptote. Okay? That's called an asymptote. Okay, so a horizontal asymptote is basically a line that you can draw on a graph, and you start to get closer and closer to it as you head to the right or the left. These are both examples of horizontal asymptotes. Some people think with horizontal asymptotes you can never cross it. No, that's not true. You can cross it. But what happens as you get further and further to the right is you start to close in on it. Okay, you start to get closer. So with asymptotes, we don't care what's happening in this area. We care what's happening way over to the right. Are we getting closer and closer to something? If so, that's a horizontal asymptote. And the picture on the left, that's an example of a horizontal asymptote that you never cross. You just seem to get closer and closer to it the further to the left that you go. Okay. And in our book on page 217, they've got more examples if you want to see additional pictures. Okay. But that's the idea. Horizontal asymptotes are generally sketched as a dotted line in our picture. So I wanted to sketch the asymptote here. I would do something like that. That symbolizes a line I get close to, but never reach. Okay, so let's look at this one. And let's see if we can find the horizontal asymptote. Okay, so first thing, when you write a horizontal asymptote, it's a horizontal line. What letter do we always start out with when we're writing the equation of a horizontal line?
Y equal.
Yep, y equals. If you accidentally do x equals, that's vertical. We haven't talked about vertical asymptotes yet. Okay, so we want y equals. And we've got to do y equals and then put a number. Yep, just scan it. Perfect, thank you. So y equals, and we got to figure out a number. We can graph it, but we don't need to graph that. Okay, we can figure out what the asymptote is without graphing. First thing you want to do is look at the part of your fraction that has an x in it. We'll come back to the +2. To find the horizontal asymptote, let the x value get really big, okay, and plug it in. So what I want you to do is imagine plugging in infinity right there. Okay, so think of this. 1 over infinity. If it's confusing to think of infinity, just let infinity be like 100 million. Huge number. If you take 1 and you divide it by something that's huge, what happens? Yep. It gets really, really small. So what's in this box is going to start to get really, really, really small as x gets really, really big. when you take something and divide by infinity, we just said it's getting smaller, but what's it getting close to? It's never reaching, but it's getting very close to what? This is getting very close to 0. It's basically 0. It's getting very close to it. And if you take something that's extremely close to 0 and add 2, you're going to get a number that's extremely close to what? Yeah, 2. 2. That's your horizontal asymptote. It's the number you're getting very close to, but you're never reaching. So if x is 1,000, you'd have 1/1000th plus 2. It's 2.001. It's very close to 2, but you will never reach 2. You just get close. Yeah, so the part that has a variable in the bottom, you can basically think of that part as just disappearing. And then whatever's left is what's going to end up being the horizontal asymptote. Okay, let's try another one. So 1 over x minus 3. So this is going to be a horizontal asymptote at -3. The part in the box, as we let x get bigger and bigger and bigger, that fraction is going to get smaller and smaller. As this fraction continues to get smaller, it approaches 0. Never reaches, but it gets very close. And 0 minus 3 is -3. So anytime you have a fraction, even if it's a different number in the top, it doesn't matter. Anytime there's a variable in the bottom, it's going to cause the fraction to get really, really small. Whether you take 3 and divide by 100 million, or you take 1 and divide by 100 million, it's basically the same thing. It's very, very small, 0. Any questions on that one? In the bottom?
On the outside of the parentheses.
So you won't have a variable on the outside of the parentheses. No, the only variable that you'll have will be in the bottom. Yeah. For this kind of problem. Okay. So let's graph that and just see what it looks like. Okay, we just said that the horizontal asymptote should be at 2. I just want to confirm that that's what happens. Okay. To type this in on the calculator, you need to do 1 over x, and then do a plus 2. Make sure you put 1 over x in parentheses. Let's do zoom 6. Let's put this over here, make that bigger. Remember, this part should keep going down, and this part should keep going up. And now let's put a dotted line in at 2 and see if that looks like a horizontal asymptote. Let's put it at 2, right about there. Okay, what do we think? Does that look like a horizontal asymptote in this graph? Yeah. Again, it looks like it's touching the asymptote because the asymptote has thickness. But remember, an asymptote is really infinitely thin. All these lines are infinitely thin, and it never actually reaches 2. Okay. Another way you can tell that it doesn't reach 2 is if you go to your table, plug in different numbers for x, and watch what happens as x gets bigger and bigger. Let's start with 10, 2.1. Let's go out to 50. So we're going further to the right, 2.02. Let's go all the way to 400. 2.0025. So you can see as x is getting bigger, I'm getting closer to 2, but I will never reach it. Okay? No matter how big I go, it's just going to get closer to 2. Okay? Eventually, if you go big enough, it's going to start to write it in scientific notation. Okay, so it hasn't yet. Let me do 50,000. Well, it didn't use scientific notation here, and it did say 2, but watch what happens if you highlight it. 2.00000. It ran out of decimal places, didn't have enough space on the screen. So don't think that it actually reaches 2. If you highlight it, you'll see that it doesn't. And eventually, I think it will start to use scientific notation. No, it's not. It's just putting in a bunch of zeros. Any question on that one? Let's look at this one again. So same graph we had when we did this first one with the horizontal asymptote, but this time I don't want to look at what happens as x gets bigger. I want to look at what happens as x gets close to the number you're not allowed to use. What number are you not allowed to plug into the bottom? 0. Okay. So let's put that in. 1 over x. Okay, I'm going to get rid of the numbers I just typed in. So we're not allowed to use 0. Actually, look at right there. I just changed it to scientific notation. It wasn't scientific notation. I don't think it was a minute ago. So sometimes it will change it. Okay, so let's see if you plug in 0. Well, it says error, because you can't plug in 0. But let's plug in something close to 0. What's a number that's really close to 0? Yep. 0.1. Right? If you plug in 0.1 for x, 1 divided by 1/10, that comes out to 10. Right? Let's go even closer to 0. 0.001. That's 1 divided by 1/1000th. That's 1,000. What's happening as I get closer and closer to 0? What's happening to my y value? It's getting higher, right? I mean, now I'm up at 100,000. Okay? The closer and closer I get to 0, the higher and higher the y value starts to go. What do you think the y value is approaching? Infinity, yes. So as x approaches 0 from the positive side, okay, what does that mean? Positive side is on the right. That's where your positives are. So approaching 0 from the positive side means start somewhere on the positive side and then start heading to the 0 this way. Okay, it's coming from the positive side. Now, I want to also look at it coming from the negative side. That means start on the left and approach 0. What happens to your y value if you start on the left and start heading to the right? It decreases. The y value starts to go down and it never stops. Okay, so here's the notation that describes that. This notation means as you approach 0 from the positive side. Approach 0 from positive side. So start on the positive side and head to 0. This notation means approaching 0 from the negative side. That's why it has a little minus. Okay, so there's 2 different ways you can approach 0. You can come at it from the positive side, or you can come at it from the negative side. And depending on which way you come at it, different things are happening. Approaching infinity or negative infinity. Any questions on that? Whenever you start to approach a number, like 0 in this case, if you head up to infinity or down to negative infinity, which we're doing both, that is called a vertical asymptote. So the kind of graphs that we're looking at right now can have 2 different kinds. One's horizontal, the other one is vertical. Okay, so in general, how do you figure out when you have a vertical asymptote? If you're looking at a graph, and as you approach a number, all of a sudden your graph starts to curve up and it never stops, or if it curves down and never stops, that number that you're approaching, that is your vertical asymptote. And when you write the equation of a vertical asymptote, make sure you always do x equals. Because x equals is for a vertical line, y equals is for horizontal. Okay, so how do you figure out the number that you're not allowed to use? It's whatever would cause you to divide by 0. That's how you figure out where your vertical asymptote is. It's the number that would cause you to divide by 0. So if I were to graph, let's say, something like this. Y equals 1 divided by x minus 2. What number am I not allowed to plug in for x in the bottom? 2. So watch what happens when I get close to 2 over here. All of a sudden, when I get close to 2, my graph curves up and down. That's because 2 is a vertical asymptote. And that will always work as long as you do not have any common factors in the top and the bottom. Okay, let me show you what I mean by a common factor. Let's take this and let's modify it so instead of having just 1 in the top, let's make it x minus 2. Okay. Now there's a common factor in the top and the bottom. The top has an x minus 2. The bottom has an x minus 2. What number are you still not allowed to plug into the bottom? 2. When you plug 2 in the bottom, you get 0. But what about when you plug 2 in the top? You also get 0 there. When that happens, you will not get a vertical asymptote. Watch what happens as you get close to 2. First, we're dividing two things that are identical. What do you get when you divide two things that are the same? 1. Okay? So you're going to get a horizontal line at 1 when you graph this. But watch what happens when you get close to 2. What does it look like happened when you got close to 2 right there? Nothing. It doesn't look like anything happened at all. If we zoom in, let's see if we zoom in on 2 and see what happens. Okay, I still don't see anything. But if I trace to 2, it's definitely not giving me a y value. The y value is blank because it can't give me one. For different values, it's giving me the y. Let's zoom in again. See if we can see anything. Maybe we will, maybe not. Okay, so I'm not seeing anything. No matter how much I continue to zoom in, it just looks like a connected line. But we know when you plugged in 2, it did cause you to divide by 0. And my point of zooming in over and over is to show you that there is a problem in this graph. But no matter how much you zoom in to 2, you're not seeing it. And I've zoomed in quite a bit. I'm still not seeing it. Look at my window. My x min is 1.99 and my x max is 2.00. I mean, I'm zoomed in a lot. My whole screen is only 0.01 units wide at this point. But you're not going to ever see what's happening there. Okay. When you have a common factor and you try to plug in a number that causes you to divide by 0, you get what's called a hole in the graph. So if I was going to sketch that graph and show you what it looked like on paper, I would do it like this. It looks like a horizontal line, but there is a tiny, infinitely small hole in the graph. And no matter how much I zoom in, I can't see it. Okay? So that's why factoring is important. So let's say we had something like x squared plus 5x plus 4 divided by x plus 1. Okay. What number are you not allowed to plug in for x? Right, you can't plug in -1. So now we know -1 is undefined, but the question is one of two things. Is there a vertical asymptote that we're going to be able to see, or is it where you have a hole in the graph and you can't see it? Well, factor the numerator. That's going to factor as x and x plus 4 and plus 1. Do we have a common factor in the top and the bottom? Yes, we do. Because there's a common factor, I agree, you cannot plug in -1, but you will not get a vertical asymptote. You will get a hole in the graph at -1. It's infinitely small, and you can't see it. So this x plus 1 is going to cause a hole in the graph at -1. That's what would happen. If it asked you for the vertical asymptotes in this problem, you would say none. There will not be one. Now, if I can graph it real quick and show you. So let's graph x squared plus 5x plus 4. You don't even have to factor it. The calculator will figure that out. And watch what happens when you get to -1. Let me zoom back out. -1's right about here. Doesn't look like anything happened at all. It went right through it without a problem. Now, let's make it so the top doesn't factor as that. Mess the top up. So now the top doesn't factor as x plus 4, x plus 1 anymore. Because I changed the number, I just messed up the factoring. So let's see what happens at -1 now. You're not going to have a common factor anymore. And now you can clearly see the asymptote again. So that's a vertical asymptote right there. All right, so let's try to find the vertical asymptote on this one. First, always start with x equals. And is there a common factor in the top and the bottom here? No. You don't have an x minus 2 in the top. That would be a common factor. So what value would cause you to divide by 0? 2. That's your vertical asymptote. X equals 2. Okay, let's look at this one. Is there a common factor in the top and the bottom of that fraction? No. You need an x plus 3 in the top to have a common factor. We don't have that. So what would be your vertical asymptote in this case? -3. Yep. This minus 1 at the end, that doesn't have anything to do with a vertical asymptote. Horizontal, yes. Horizontal asymptote would be at y equals -1. But the vertical is just what causes you to divide by 0. And that has nothing to do with the bottom of the fraction. Okay. Any questions on that one? I don't think we need to graph that one. All right, let's look at this one. It says find the horizontal and vertical asymptotes, and we want to describe the transformations. Okay, so this would be a good spot for me to make a diagram that shows you your transformations. First of all, that's not in what we call standard form. Standard form has to look something like this. 1 in the top. You can have a number in the bottom in front of x. You can have plus or minus a number times a number, and then plus a number or minus a number on the end. I'm going to describe what each of those 4 boxes do. Some of them shift, some of them stretch. Some are horizontal, some are vertical. And there's a certain order we always have to follow when we describe each box. You go in alphabetical order, A, B, C, and then D. Both A and B are going to cause things to happen horizontally to the graph. A is going to be a horizontal shift. We've got to know which way it's going to move them. Anybody have a guess when it's positive, which way it's going to move horizontally? Left, yes. You might think positive is right, but horizontal is always, it's kind of backwards. So positive is going to go to the left, negative moves it to the right. Okay. If A is the horizontal shift, the only other option for inside here, it's still in the bottom of the fraction, so it's still horizontal, but it's the stretch. And I'll do an example. Let's say B was 1/2. So, if B was 1/2, you might think 1/2 is a small number. Small numbers make it smaller. Nope, it's actually the opposite. If B is 1/2, this is a horizontal stretch by factor of 2. 1/2 actually doubles it. 1/3 would triple it. 1/4 would quadruple it. If you want to compress it, so let's say if B equals 5, you might think, oh, big number makes it bigger. No, big number actually makes it smaller horizontally. That's going to compress it 5 times as much. Or you could say stretch by 1/5. Stretching by 1/5 shrinks it. Horizontal stretch by 1/5. Okay, so that describes all the horizontals. Now the stuff on the outside, that's your vertical. Do you think C is going to be a vertical stretch or a vertical shift? It's going to be a stretch. Anytime you multiply, which is what B is doing, it's always stretching. And C is multiplying, so that is stretching as well. So vertical stretch. There's nothing backwards about this one, so I'll just do one example. If C equals 3, you just say vertical stretch by factor of 3. Vertical stretch by factor of 3. If C was 1/2, you'd say vertical stretch by factor of 1/2. Okay, so we got that, and then the last one is D. What do you think D is going to be? That's your vertical shift. Anytime you add or subtract, that is always a shift. If it's in the bottom of the fraction, it's horizontal. If it's on the outside of the fraction, that's your vertical. So vertical shift. And nothing backwards about it. Positive is up. Negative is down. Okay. 2 notes about B and C off to the side. If B is negative, this causes a, well, do you guys remember what a negative does to a graph? We looked at it when we did quadratics. It flips it, yeah, it's going to reflect it. So if B is negative, that's a horizontal reflection. Or you could say reflect over the y-axis. This is what a horizontal reflection would look like. Horizontal flips left to right. Horizontal reflection. And then if C is negative, what kind of reflection do you think that will be? Vertical, because C is vertical. So a vertical reflection would look like this. That's up to down. That's a vertical reflection. So if C is negative, vertical reflection. You can also say reflect over the x-axis. Okay, so that chart, that diagram right there, that describes all the different transformations. But it assumes that your problem, like this, is in that format. This one's not. So we've got to fix this one so it is. So that's going to go back to what we did last week. I don't think we did synthetic division, but we did long division, right? Yeah. In here? So that's what we need to do. Let's use long division on that and rewrite it. Okay, so x minus 5 goes on the outside. 2x minus 13 on the inside. Okay. Take 2x, divide by x. What's 2x divided by x? 2. Multiply it back out, and then we're done. 2x minus 10. What do we do with those columns when we do long division? Subtract. 2x minus 2x is gone. What's negative 13 minus 10? It's going to become negative 13 plus 10, which is negative 3. What do we call this part of my answer right here? That's my remainder. And what do we call that part? Quotient. When you write your answer with long division, this is how I showed you to do it. Quotient plus remainder. Could be minus remainder if your remainder was negative, but quotient plus remainder over the original denominator. So my quotient is 2. My remainder is a negative number, so this is going to end up being a minus. Minus my remainder over my original denominator was x minus 5. So now what's in black right there and what's in green right there are exactly the same thing. But this in black is a little bit closer to that. Okay, so a couple things we got to do to fix that. First, when it's in standard form, what number is supposed to be in the top of the fraction? We're supposed to have a 1. So when you have a fraction, let's say you had 3 over x, you can easily make a 1 in the top by doing this. Because what's 3 times 1? 3. And that's exactly what you had right there. So you can just put a times 3 in the front. Right? And that we usually put on the right side. So let's fix that. So I'm going to put the 2 over there. I'm not moving it to a different side of an equation. I'm just putting plus 2 on the end instead of plus 2 at the beginning. And I'm going to put the 3 in front with that negative that's already there. Now, that's exactly in the format it needs to be. There are 4 transformations in this one. 1, 2, 3, 4. We just have to describe what each one of them does. Okay, let's start with what's in box 1. Minus 5. What's that minus 5 going to do? Horizontal shift. Which way? To the right? How many? 5. So that's the first step. Shift right 5. Okay. What about box 2? That's a times 3.
It's vertical stretch. Approximate 2.
Vertical,
Just straight.
so vertical stretch, what else do we have to say?
Oh, and vertical reflection.
That's going to be the next step. So we don't have to say anything with
Oh,
the negative
vertical
yet.
stretch by factor of 3.
Yes. Perfect. Vertical stretch by factor of 3. And now you already said the next step, a vertical reflection because of what's in box 3. And what's going to be my last transformation?
Up to.
Let's see. Yep, shift up 2. Okay, so that takes care of describing how the function can be obtained from the original, all the shifting and stretching. The last thing they do want are the 2 asymptotes. Okay, so horizontal always starts out with what letter?
Y.
Yep. And vertical? Okay, so at least if we get that right, we're off to a good start. And now the horizontal. Look at, let's go back, let me zoom in on this. Look at this problem. Focus on this fraction first. If x was 1,000,000, and you take away 5, and then you do 1 divided by that, this fraction is going to get very close to what number? What is it?
5.
So just forget about everything else, just this fraction. So take 1 and divide by 1,000,000 minus 5. So you take 1 and divide by 999,995. It's very, very close to what? Very close to 0. And if you take something that's very close to 0 and times it by -3, what do you get? About 2.
What was the question?
If you take something that's close to 0 and multiply it by -3,
Multiply by -3, and you get something. Is that still pretty close to 0?
still pretty close to 0, yep. And then if you take something that's still pretty close to 0 and add 2 to it,
Then it's pretty close to 0.
pretty close to 2. So this is the number that is going to affect your horizontal asymptote. It's the only number you have to look at. And it's y equals 2. Okay, let's put that down. And vertical asymptote. What would cause me to divide by 0 in this case? 5. That's my vertical. Okay, so that's describing the transformation. So this chart, very important. And then the asymptotes. When we had to do the long division, that's probably about as complicated as they'll get. Okay, you're not going to have to do long division where it ends up being like 7 or 8 steps. That's about the difficulty this week. Any question on that one? Okay, so last problem. So this is going to be a mixture problem. When we're given a mixture basically is going to have a concentration to it. So like when you have a chemical, if it's 100%, then that means what you have is just that chemical. If it's 50%, then maybe your mixture is 50% chemical, 50% water. It's not all the chemical. If I gave you a solution that was 50 ounces and said that 35% of it was acid, the other 65% of it is just water. Out of the 50 ounces, how would you figure out how much of it is actually the chemical? So you've got 50 ounces, but only 35% of that is actually the acid. Yeah?
You multiply 50 by 0.35.
Yeah, you basically just have to find 35% of 50. So that means out of the 50 ounces of volume you have in front of you, only 17 and a half ounces of it are acid, and maybe the rest was mixed with water. Any question on that stuff? So when you want to find a concentration, it's the same way you figure out your grade on a test if it's based on how many questions you get right. In the bottom, you always put the total. In our case, it's not the total number of questions on a test, it's the total liquid. And in the top of your fraction, if you were looking at a test, it would be how many questions did you get right? That's the part I'm interested in. Well, in this case, I'm interested in the total acid. That's how you figure out the concentration. Find the total amount of acid and divide by the total liquid. So if I gave you 100 gallons and 30 of it was acid, that's a 30% solution. 30 out of 100 gallons. 30 out of 100. Okay. So let's set this one up and see if we have time to solve this. So we're going to take that same solution that we had before, 50 ounces, and right now it's at 35%. I'm going to take and I'm going to pour X ounces of 100% pure acid into this mixture. So if I do that, what's going to happen to the concentration of my mixture? It's going to go up. It's going to get stronger. Okay, so I'm trying to make it stronger. I want to find a graph of the new concentration. Okay, so let's use our formula. Concentration is the total acid over the total liquid. And the concentration is going to be a function of how much I pour in. The more I pour, the higher it gets. Let's do the bottom first. Total liquid. Well, the total liquid is made up of two things. One, how much liquid did I start with in my mixture? We started with a 50-ounce solution, but we're pouring more in. How much more am I pouring in to the mixture? I'm pouring in X ounces. So I started with 50, I'm pouring in X ounces. That's going to be my new total amount of liquid. Now in the top is the total amount of acid. How much acid was in this solution to start with? I had 50 ounces, but it wasn't all acid. Yeah?
17 and a half.
Right, we started with 17 and a half. And how much acid are we pouring in? We're pouring in X. That is the graph of your concentration. Okay. So let's graph it. 17.5 plus X divided by 50 plus X. Now, concentration is always between 0% and 100%. This is a decimal. So it's going to be somewhere between 0 and 1. If I multiplied by 100, I could make it 0 and 100. Am I taking acid out? Like, can I pour in a negative amount? No. What's the most amount I could pour in? There's no limit. I can pour in as much as I want. So look at my concentration. It's getting higher, but how come it never reaches 100%? There's still some water in it, right? The way I sometimes explain it is like if you got a big gallon container of paint and you put a drop of green in white paint, that drop of green is always going to be in there. You can add more white to it, but you can't take the green back out. It'll never be 100% white again. It'll always have a really small amount of green because you put a drop of green in it. right? So your concentration here can never hit 100% because you didn't start with something that was 100%. Okay. And that's our formula. So we'll stop with that, and then tomorrow we'll finish up the last thing with that. Okay, the last thing is to graph a horizontal line and see where they cross. But we'll do that tomorrow. Okay. So that's the homework for tonight. 48A and B, that's the mixture problem. You should be able to do 48A. We might have to do 48B together in class.